So thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Meghal Gupta, who will tell us about few single qubit measurements suffice to certify any quantum state. So Meghal is a fourth-year graduate student in the UC Berkeley EECS department, advised by Professor Venkatesan Guruswamy. So she enjoys working on different areas of computer science, which include quantum computing, error correcting codes, and streaming algorithms. So Meghal, the floor is yours.
Okay, thank you so much for introducing me and also for inviting me to give this talk. The work I'm going to be presenting on is called Few Single Qubit Measurements Suffice to Certify Any Quantum State. This is joint work with William He, who's a third-year graduate student at CMU, and Ryan O'Donnell, who's a professor at CMU. Cool. Okay, so let me start by defining the problem of quantum state certification and motivating it. So one situation that might come up is that there's some quantum state psi on n qubits that you know about, but you want to prepare in the real world. So maybe we have some candidate process outputting that's trying to prepare psi. So it's outputting copies of some state that you hope is psi, but you're not sure. So then you want to have an algorithm to check if indeed this black box is actually outputting copies of psi rather than some other candidate state. So that's the problem of certification. Given a state rho, you want to check whether or not it's actually equal to psi. So I guess more formally, what you want to satisfy the requirements that if the two states are actually equal, then you accept, and if the two states have fidelity at most 1 minus epsilon, then with probability at least 0.99, you want to reject. So does the question of quantum state certification make sense? I guess since I can't see everyone, it's better if people say yes or no.
Yes. Okay. Someone.
In your setting, the target state will be pure state.
Yeah. So the target state is a pure state, but the lab state might be a mixed state. It's, I guess, useful to think of it as a mixed state, largely just because it could be a okay, first of all, mixed states exist, and also because it could be a probability distribution over pure states. The reason that the target state has to be pure is this is known to be impossible to do efficiently with only single qubit measurements if psi is mixed.
I see. Thank you.
Okay, cool. So I guess before we get into the concept of single qubit measurements, this problem as I've stated it is really easy. All you would have to do is measure in any basis, measure rho in any basis containing psi, and accept if and only if all the outcomes are psi. And you can do some easy analysis to show that you need 1 over epsilon copies, and that this is the optimal algorithm. So the question is, I guess, why is this not a good algorithm? The reason that this isn't a good algorithm is that performing a measurement in this basis containing psi, this POVM that I said here, is basically as hard as preparing psi. And the entire reason we wanted to do certification was because we wanted to see if this black box that prepares psi actually works. So it's so it's a little bit backwards to think that we could have the ability to prepare psi as well. We kind of made no progress if we're requiring the ability to prepare psi in order to check our black box that's preparing psi. What we actually want is a much simpler way to check if rho is equal to psi than it would be to prepare psi in the first place. So that sort of leads to the question, can we certify using only much simpler measurements and not measurements that require preparing psi in the first place? So one question we can ask, the most basic form of measurements are single qubit measurements. So can we certify whether rho is equal to psi or not using only single qubit measurements? So these would be measurements where you take rho, you measure 1 qubit and then you measure 1 qubit at a time, rather than measuring the entire thing all at once, which could be exponentially complicated to set up. So does the question make sense? Okay, I'll just assume yes, because I can't see anyone.
So when you say single qubit measurements, like you don't care whether you measure them at the same time, in parallel, or sequentially.
Okay, that's like a great question. That I was deciding whether to put that here at the end of the talk, but like our algorithm requires adaptivity, which means you have to measure the first qubit and then based on the outcome, like choose a basis for the second qubit and so on. This is definitely like a big caveat to applying this algorithm in practice, because I think like adaptive measurements are not all that practical. But we do also have a result in our paper that shows there exists state psi that you cannot certify with like non-adaptive measurements. So you do actually need the adaptivity for certain states. And I think an interesting question is sort of to figure out like how many rounds of adaptivity you need, or like can you broaden the classes of states that we know how to certify without adaptivity, since those are probably the most practical algorithms for certification.
Okay, I see. Yeah, thanks.
Yeah, but the algorithm I'm going to present is very adaptive, and you do have to like measure them sequentially and not like in parallel, because you don't know the basis you're going to want to measure them in advance. Okay, so right, so the main question is, which I guess I've already sort of given away the answer to, is what state psi can we certify with single qubit measurements to only a few copies of rho? So I guess this question has been studied for a while, and all previous algorithms like didn't sort of give a full answer to the question. So a number of them work for only a restricted class of states or noise models. One notable work was the recent work of Huang, Preskill, and Soleimanifar in 2024, which proves that like for random state chosen via the Haar measure, you can in fact certify it just with the very, very simple algorithm of like measuring in the measuring in like the computational basis and then measuring one of the qubits randomly after that. Or measuring all but one of the qubits in the computational basis and then measuring like one qubit in a random basis. And there are other works that work for all possible psis, but then like need exponentially many copies in the worst case. So this work answers the question definitively and says that there actually is an algorithm for every state psi. So the theorem is that there's an algorithm that, given the description of any n-qubit target state psi and n over epsilon copies of the lab state rho, makes single qubit measurements to rho and certifies whether or not rho is equal to psi. And here like certifies whether or not it's true, as in the previous slide, where you want to accept if they're exactly equal and reject if they're at least 1 over epsilon, if they're at least epsilon distance apart in the like infidelity measure. I'll also make a quick note here that you don't need that your algorithm doesn't require that they're literally exactly the same to accept, but this algorithm is going to be a little bit tolerant, and it will accept as long as the states as long as rho and psi have fidelity at least 1 minus epsilon over n. But we're not going to focus a ton on that distinction for the sake of this talk, because it's not as like illustrative of the main point of the algorithm. Okay, so we're actually going to phrase the theorem this way. So I think this is like the right theorem to keep in mind, and this is like the theorem we're going to focus on trying to prove during the talk. So the algorithm we're going to present does the following. It takes in the description of psi. It takes in one copy of the lab state rho, measures each qubit of rho once, and accepts with probability at least the fidelity squared, and then rejects with probability at least the infidelity over n. And if you apply this theorem to n over epsilon copies of of rho, then you'll recover the previous theorem. So like this theorem plus amplification gives like the theorem on the previous slide. I'm going to pause for like 10 seconds here to make sure that this theorem statement makes sense, and then I'll move on. And like definitely ask questions while I'm paused.
Sorry, in your setup, I saw you want to accept with probability 1, right? And then you reject with probability higher. Like, is that true?
Yeah. So if the states are truly equal, you want to accept with probability 1. And indeed, like in that case, the fidelity is going to be 1.
Okay.
If you want a little bit of tolerance, like you want to say, I want to accept with probability basically 1, if the states are in fact 1 minus epsilon n apart, you can just still apply this many times and then like accept if the number of rejects was sufficiently low. So you could amplify it if you wanted to be a little bit tolerant, like if you wanted to accept if psi and rho were really, really close. But yeah, I guess as it's stated, like you can get all of those results or any sorts of those results by proving this theorem. But this theorem, but yeah.
Oh, you're muted.
Wait, I'm muted?
No, Taiga is asking.
I have a question. So, so if you amplify the accept and reject error, then I think we need to amplify. So we need to run many times this protocol, right?
Mm-hmm.
So in this case, should we need to assume that rho is identically sampled?
Is what?
So I mean, rho is how rho is generated. So I mean, rho is supposed to be generated by identical process, or not?
I guess because I guess the way I stated the theorem on the previous slide, it makes it sound like rho does need to be identical every time, but since you're just using this theorem, since you're just amplifying, it doesn't actually need to be. So I think you don't actually need that property. Like it's okay if they're not drawn, if like each of the rows are not drawn from the same distribution, as long as like when you're doing the amplification, you'll have some criteria like on average the fidelity was lower, high, and then you'll accept or reject.
I understand. Thank you.
Yeah, just quickly, I guess you'll clarify this later. But so the algorithm is adaptive as you measure every qubit, seems to be, but it's not adaptive across many copies.
Yeah, it's not adaptive across the copies. So you can do each of the, you can do like all of that in parallel. Okay, cool. So now I guess we'll spend most of the talk proving this theorem. Without loss of generality, we'll assume that rho is a pure state. The reason this is without loss of generality is that like a mixed state can be viewed as a classical distribution, a classical probability distribution over pure states. And then if you prove this theorem for like any pure state, then you can prove it for all mixed states by like averaging over all the pure states in the distribution and then using linearity of expectation. So from now on, rho is always going to be a pure state. Okay, so I guess the next thing to do is just like to state the algorithm. So the first step of the algorithm, we'll just choose some k and n uniformly, and then the first real thing we'll do in the algorithm is we measure the first k minus 1 qubits of the lab state, and then get some reduced state lab x. So, and then we're going to and then the rest of the test is sort of going to be doing something with this reduced state lab x. And then so we do some stuff, and the stuff is going to be some subtest that checks whether some specific property of lab x matches psi x. So we have the state lab x in real life, and then we have the state psi x in theory, and we want to check whether some property of both of those is the same. And the specific thing we're checking is whether lab x0 and lab x1 relate to each other in the same way that psi x0 and psi x1 do. I'm not going to elaborate on what I mean by that quite yet, but the point is just that we're going to be running some subtest that checks some property of lab x and psi x and sees whether they are the same. So you can think of this as sort of we have a tree. We in this case n equals 3. We choose a k. In this case, we chose k equals 2, which means we measure the first qubit. Maybe we get the outcome x equals 1. And then on the rest of the test, we're going to be running on lab x, which is the node of the tree indicated here. And then the specific thing we're going to test is something about lab x0 and lab x1, which are the two children of it. So does this setup kind of make sense? At least in terms of vibes. I haven't really been super specific about what exactly the subtest is.
Yes, can I just ask a question about the protocol? Is the protocol inefficient in time, in runtime?
So I think that depends on what kind of access you assume you have to psi. So like, I guess it's a little bit hard to talk about classical efficiency because like it's possible that like any description of psi is just going to be like super long already, or like is just like you can't write necessarily just by counting argument, you can't write down all psis like in reasonable amounts of time. So the question is like, what's the right model to define? The way our algorithm,
well, I mean, you could describe it as a quantum circuit, for example, right?
Yeah, but even that could require like exponentially many nodes, right? Like for the worst case side, that requires exponentially many nodes. So the question is like, what are we sort of comparing our classical runtime to like, okay, if we have a circuit of this, one reasonable comparison point would be if we have a circuit of this size, then our algorithm is like at least this sufficient or something like that. Or we have sort of like classical Oracle access to like query certain properties of the state. So our algorithm will require us to be able to query the amplitudes of psi in any product basis.
Okay. Cool, thank you.
And I think it also, sorry, it's a little bit more specific than that. It also requires querying the amplitudes of any like, if we measure, I guess like if we measure the first like, if we measure like any subset of the qubits, we need to be able to query the amplitude condition on getting a specific outcome for like that subset of the qubits in any specific basis. So it requires like a decently powerful classical oracle for like access to psi. And like, I think it's a reasonable question to ask, like, can you like design an algorithm that requires like, that like is more classically efficient or like requires a less powerful classical oracle to psi when like dealing with like classical runtime.
Okay, great.
Okay.
Thank you.
Cool. Yeah, so I guess looking at this, the ultimate plan is going to be that we run this subtest, and then that subtest is going to have some probability of rejecting if like lab x0 and lab x1 are not related to each other in the same way that psi x0 and psi x1 are. And then then we're going to hope that like, you know, if we run this test for like sort of a random x chosen by how we're choosing x in steps 1 and 2 of our algorithm, then on average, if lab and psi are far apart, then this algorithm will reject. So in order to like sort of quantify that a little bit better, I'm going to, for the rest of the talk, use the following notation to denote psi x and lab x. And then we're going to define the quantity of x. So I'll stop after a second after I explain a little bit more, but the main thing that we're going to prove is that the probability that the subtest on x fails, that should be subtest, not subtext, is going to be at least some quantity called of x. And then we will show that we will show two things. If indeed we can design a subtest that fails with this probability, then the overall test is going to have to fail with probability at least infidelity over n. And also that we can design this subtest that fails with at least this probability. I'm going to pause for like, I think 10 seconds here for you guys to process what this new notation is. In some sense, like you should, if you look at of x, like it sort of captures a little bit about what I was saying on the previous slide about how it's capturing if u0 and u1 relate to each other in the same way as v0 and v1 do. I think it's easiest to like look at this equation and like first don't look at like assume that u0 and u1 are the same magnitude, and then see how this basically just captures whether there's like a phase shift, but a phase difference in how u0 and u1 relate to each other versus v0 and v1 relate to each other. That's like, I guess, an example of one thing it captures.
Sorry, can you just clarify what u0 and u1 are? Are they just are they orthogonal states or?
They're not necessarily orthogonal states. I'm just writing. I'm just expanding out psi x by like expanding the first qubit in the computational basis, and then having u0 be like the rest of the state condition on like the outcome.
Okay.
the outcome like 0 on the first qubit.
And you're absorbing the coefficients into them as well.
Yeah. I guess I should also note that U0 and the U's and V's here are not unit vectors. Everything in kets will be, throughout this talk, will be unit vectors, and everything not in kets does not necessarily have to be a unit vector. Okay, cool. So the two things we need to prove are like, we need to actually design the subtest, and we also need to prove that if we have a subtest that fails with at least this probability, then we're done.
Sorry, can I just check one more thing? Your, like, the right-hand side of psi x doesn't depend on x. Can you comment on that?
Okay, I guess maybe another, or sorry, psi x is just going to be expanded as 0 and 0 tensor U0. U0 does depend on x. So it's possible this should have been, I guess, like maybe a clearer notation would be to write U0, instead of writing U0, write like UX0. But now that x is fixed, for like after we run steps 1 and 2 of the algorithm, x is fixed. So I guess it's simpler notation to just like drop the x. Does that make sense?
Okay, maybe I missed how x depends on how the right hand side, how does u depend on x, u0 and u1?
We're just defining u0 and u1. So we have some state psi x. We're just defining u0 and u1 as like what they would be if in order for this expansion to work. Like psi x is some state, and I'm just like writing it in a different form. I'm just writing it as 0 tensor u0 plus 1 tensor u1. And like obviously for if psi x were different, then if x were different, then u0 and u1 would be different.
Okay, cool.
So it's just the expansion, and like we're fixing x for the entirety of the talk now, or like okay, so the two things we need to do are like design the subtest and show that if we design the subtest, we're done. So the second part is easy. We can just literally write out like a 3-line expansion and show that indeed the expectation of this quantity when x is drawn by first choosing k uniformly at random and then measuring the first k minus 1 qubits of lab in a computational basis, which is exactly what which is exactly what steps 1 and 2 of our algorithm on the previous slide did, then this quantity like sums to exactly the infidelity over n. Okay, so the rest of the talk basically is going to be like dedicated to proving dedicated to actually designing the subtest. So we want to design a subtest that given n minus k plus 1 qubit state lab, given the state lab x, measures it and rejects with probability at least error of x, and accepts if lab is equal to or lab x is equal to psi x, because like you don't just want to design a test that always fails. So for the intuition, let's do an example. So let's take our example to be x is equal to like the empty string, and then psi is equal to the 0, 0 plus 1, 1 state. And we want to differentiate this from the case where lab is equal to 0, 0 minus 1, 1. So in this case, if we evaluate our x, we get 1, which means that like indeed our subtest, in order to be like a good subtest, would have to like differentiate these cases. In fact, differentiate them with probability 1. So the question is like, how do we detect this like minus sign error? So I guess like one way to, this isn't the only way to structure a test, but like the way we're going to talk about structuring like this sort of test is the following, because this is what's going to be most useful for generalizing this. We want to get this error to show up on the first qubit by measuring the second qubit in a basis that will like push up the discrepancy to the first qubit. So what we're going to do is we're going to measure the second qubit, and then we're not going to take any like information out of that measurement. But then after we do that, we're going to like run a test on the first qubit and hope that the minus sign hope the fact that there was a minus versus a plus sign like will show up when we like measure the first qubit in like an adequate basis. Does that like plan sort of make sense? Or I guess maybe I won't ask too much clarifying questions here because like it'll probably make a little bit more sense when I explain this. So let's say that we measured the second qubit let's say we tried to run this test by first measuring the second qubit of the lab state in the computational basis, and then we were later going to like run some test on the first qubit to figure out whether we were in psi or lab. This like can't work, because if the outcome on the second qubit were 0, then the first qubit is now in the state 0, regardless of whether we have psi or lab. And if the outcome was 1, then similarly, the first qubit is now in the state 1, regardless of whether we have psi or lab. So there's no test we can run to differentiate the two cases, because in both cases, like the reduced state on psi or lab is like the same. So the reason that happened was because like our measurement like killed the minus sign. When we measured the second qubit in the computational basis, we, regardless of whether we got a 0 or 1, we killed one of the purple or brown components. We like only left one of them alive. We needed a measurement. What we need is a measurement of the second qubit that keeps a bit of the purple and the brown alive in both cases, because then like we can run a test on the first qubit that will detect if they're like in phase with each other or not. So suppose instead that we measure the second qubit of the lab state in the Hadamard basis. Then if the outcome is plus, now the reduced state on psi is going to be plus, and the reduced state on lab is going to be minus. And if the outcome is minus, then if you do the calculation, the reduced state on psi is minus, and the reduced state on lab is plus. And so actually, like now running a test on the first qubit will allow us to tell the two cases apart. And in general, the like higher level of why this algorithm works is, of like why this like basis was a good measurement, was because the Hadamard basis was fair towards lab 0 and lab 1. It like, regardless of which outcome we got, we let's see, regardless of which of the two outcomes we got, purple or brown, we like kept a little, sorry, regardless of which of the two outcomes we got, like plus or minus, we kept a little bit of the purple and brown alive in both cases. And so then when we measured the first qubit, there was still a phase risk difference that was left for us to detect when we like actually ran our test on the first qubit to detect whether like the state was in fact, the lab state reduced to the first qubit was in fact what we expected it to be or not. So does this like general intuition make sense?
Yes.
Okay. In that case, the intuition has been acquired and we can move on to the general case. So I guess we basically already said the criteria that we want in the general case. In the general case, we want to measure the last n minus k qubits in a basis in which both U0 and U1 are phase states. By phase states, what I mean is that we want to measure U0 and U1 in a basis where every outcome is equally likely. So we're going to, I guess, we're not worrying for a second right now about the fact that T needs to be implemented with single qubit measurements. We need each of the 2 to the n minus k outcomes to be equally likely. And if that's true, then regardless of which outcome we get, we can keep a little bit of both the purple and brown alive, and then that will allow us to sort of like detect whether U0 and U1 like relate to each other, like have the same relate to each other in the same way that V0 and V1 do, and we'll be able to detect discrepancies that look kind of like the phase difference that we discussed in our example. And in particular, we would want to show that we would capture like anything that of X captures. So I guess we'll let T be any basis that satisfies this property, that U0 and U1 are both phase states, i.e. like for U0 every outcome is equally likely, and also for U1 every outcome is equally likely. And then we'll show that if T is any phase basis, then the algorithm I'm going to describe on the next slide succeeds. And then after that, we'll show that we can like find some T satisfying this property that we can like implement measurements in, like that we can implement measurements in efficiently. So the algorithm that we're going to the algorithm that we're going to do for the subtest is measure lab X and measure the last n minus k qubits of lab X in the basis T. Then this part requires no like measurement, no like quantum measurements, but we're gonna let the single qubit state psi prime be the reduced state of the kth qubit, like the remaining qubit. If like, you know, if we actually truly had psi prime, or if we truly had psi and not lab, and then we want to measure the kth qubit of lab X in the psi and then we basically want to check at that point if the kth qubit of what remains of lab X is equal to psi prime, and the way we check that is measure in the psi prime psi prime perp basis, and except if and only if you actually get psi prime. So does this plan make sense? I think this is basic. So now we have like two things left. We actually have to like tell us how to implement in T, and we have to like figure out, and we have to like actually understand why this algorithm like properly captures everything that, like translate our intuition to equations and capture why like this actually reflects like this actually like rejects with probability at least or X. Cool. So now I guess I'll do some of the, yeah.
Sorry, I just wanted to check, like, so when you describe this basis T, is it clear that it will be a product basis?
So we haven't, so there are going to be many bases T that satisfy this property, and we haven't yet described why it can be implemented with single qubit measurements. It's not going to be a product basis. It's going to be, and this is where the adaptivity comes in. Even when we actually describe what it is, it's not going to be product based. It's going to be like you measure the first qubit, and then based on the outcome, you then measure the second qubit, and so on.
Okay.
So it will be this is where the adaptivity comes into our algorithm. And also I have not actually described how you do it with single qubit measurements. Okay, cool. So to do the calculations that say, okay, if we actually have any such basis T, then we're done. Then we can see that the acceptance, okay, so I guess like if you get any outcome L, then the reduced state psi prime would be this quantity, and the reduced state lab prime would be like this quantity that's on the slide. And I'm not going to go through the equation super carefully, so I'm not literally going to read them out or anything. But like if you just compute what the reduced states are, that's that. And you want to sort of, and then the acceptance probability is like their inner product. So if you compute that, you get the probability on the bottom, or you get like the value on the bottom slide. Or the acceptance probability, I shouldn't have said condition on L. I should have said the acceptance probability like for this L. And then if you sum them up over all the L's, you get the you get this quantity. And then like if you translate to rejection probability instead, you just have to flip the plus sign to a minus sign. And then you can like do some math to figure out this is at least err of X. And so like indeed this algorithm is going to reject with probability at least err X. And so now the main question remaining is just how do we actually like get this basis in which both U0 and U1 are phase states? Or I guess I should also ask, like, does anyone have any questions on the previous part of this before? The only thing that's remaining now is like we're going to describe how to get this basis in which U0 and U1 are both like phase states. Okay, cool. I guess I'll just explain it then. So let's start with a simple case where both U0 and U1 are 1 qubit states. In this case, it's easy. You just take the perpendicular bisector and then measure in that basis, because now for both U0 and U1, so sorry, this is the block sphere. So you draw U0 and U1 on the block sphere. You take the perpendicular bisector, and regardless of whether you get the like plus the like up green arrow or the down green arrow outcome, or sorry, for both U0 and U1, the up green arrow outcome and the like down green arrow outcome are equally likely. So you're done. So in the general case where U0 and U1 are m qubit states, you can basically just apply the same algorithm inductively. So you compute the reduced state on the first qubit, and then by using the like block sphere algorithm on the previous slide, you can find a basis that gives 50-50 outcomes on the first qubit, regardless of whether you have U0 or U1. If, for example, the first qubit is like the first qubit of U0 is a purely mixed state, or and the first qubit of U1 is a purely mixed state as well, then there's like extra degrees of freedom here. There might not be a unique perpendicular bisector, but that doesn't matter. You just need anything that like is a perpendicular bisector. And then after that, we can just induct with the two possible reduced states. So if we get the outcome 0, then we can now look at the two reduced states U00 and U01, and then find their perpendicular bisector and keep going. So this is going to be like a sort of adaptive single qubit measurement process to get the basis T. And then using this process, we can in fact measure in the basis T, and we will finish the algorithm. So let me just state the overall algorithm again, and then like I'll pause for questions. So the first two steps were we chose a layer k uniformly at random, and then measured the first k minus 1 qubits to reduce to some state lab x, and then run the rest of the test on, and then run the rest of the algorithm on lab x. Then we chose t to be some basis in which psi x0 and psi x1 were both phase states. Then we measured the last n minus k qubits of T1, or sorry, in this basis T, and got some outcome L. And then we took what psi prime would actually be if this, we take what psi would be if we had actually in fact gotten the outcome X on the first two steps, and then the outcome L on like the fourth step if we truly had psi. And then we denote that by psi prime, and then we sort of just run a quick test to check if indeed psi prime was and then we run a quick test to check if indeed psi prime was equal to lab prime. Cool. Okay, so this is a good place to stop for questions, and then I'll move on to like a little bit more future directions and stuff.
I assume this 1 on n factor that comes from the reject probability is associated with this choosing k uniformly at random.
Yeah.
Is that correct? Can you comment on why you're choosing this uniformly at random and how this affects the outcome?
Yeah. So okay. So like the fact that we're choosing k uniformly at random is like the reason that you're right that that's the reason that we're getting the factor of n. So the reason we have to choose k uniformly, I guess the reason we have to choose k uniformly at random is sort of that we don't know what lab is going to be in advance, and it's possible that lab disagrees on like, and it is possible for lab to just like not disagree on any of the layers except like, you know, the third layer or like some arbitrary layer k, and that's sort of like the only place where you see a disagreement, and therefore like I guess it's possible to have like a world where you only see disagreement on the layer k, and so you can't really like in advance without knowing what lab is like choose like the right layer to investigate and run this algorithm on. You just seeing psi alone will not give you information about that.
Sorry, do you know for a fact that it's possible that this happens, or you just haven't ruled that out?
I guess a silly example is like on a product state. If your state psi is literally a product state, then you might have the situation where only one of the qubits actually disagrees. And then like at the end of the day, this test is just running a test on the kth qubit. It's measuring like all the rest of the qubits in a specific basis, but then it's only like outputting yes or no, whether or not the kth qubit, based on whether or not the kth qubit agrees. And in a product state, like whether or not the kth qubit agrees is just going to be like whether or not the kth qubit is the same. The rest of this stuff doesn't matter, right?
Right.
So you can't do better. I guess you can't do better than choosing k uniformly at random with this test, but obviously the product state case can be done better with like other tests, and I think like it's totally possible that there's like a like natural way to unify everything that would give like a better algorithm.
Okay, great, thank you.
Does that like sort of make sense?
Yes, thank you.
Okay. Cool. So I guess the overall theorem, just to restate it, is that like this algorithm will take n over epsilon copies of a lab state row, make n squared over epsilon single qubit measurements to it, and then accept with probability 0.99 if the fidelity is at least 1 minus epsilon over n, and reject with probability 0.99 if it's at most 1 minus epsilon. So does that make sense? The next thing I'm gonna talk about is just like future directions. Okay, so we've sort of already touched on basically everything I wanted to cover here, but I'm just gonna state it anyway because I think all of these questions are interesting to investigate. The test was only 1 over n tolerant. Like on the previous slide, there was a gap between the accept world and the reject world of like 1 over n. So ideally, you'd want the test to be like more tolerant. You'd want that gap to be like a factor of 2 or something, or even like, you know, 1 minus delta. So can you do that? Can you make the test like a constant amount tolerant? It's totally possible you can. I think it's a really interesting open question. The second question is that like our test needs O of n over epsilon copies. Like this would be an even stronger, this would sort of like almost necessarily imply the first thing, but like could you do it with only like 1 over epsilon copies? If you think back to like the very first thing I said, which was that if you're allowed arbitrary measurements and not just single qubit measurements, then you only need O of 1 over epsilon copies in order to certify psi. So the question is, can you do it with only single qubit measurements? And for a while it was open. I guess before this work, it was open if you could even do it with fewer than exponentially many copies. And we showed that you can do it with linearly many copies, but but no one has even ruled out like doing it with a constant number of copies. So I guess that's a very interesting open question. And then the final thing I want to touch on is like the power of adaptivity. So as we talked about earlier, this algorithm is adaptive. Like in order to measure in the basis t, we the measurements in the basis t were adaptive. So we also have another result in this paper that this adaptivity is necessary. We show a lower bound against adversaries that make non-adaptive single qubit measurements. So basically adversaries that only measure in like a product basis. So in particular, I guess we show that we find that an n-qubit state size such that any algorithm that measures copies of measures copies of rho in a product basis will need exponentially many copies of rho to certify whether or not it's equal to psi. So the adaptivity is necessary. This does lead to a bunch of interesting questions, like can you broaden the set of states that are known to be certified without adaptivity? Can you reduce the amount of adaptivity in our algorithm? Can you strengthen the lower bound and say that any algorithm that certifies all find a state psi that you actually can you prove that you actually need n rounds of adaptivity in order to certify certain state psi? I think there's a lot of interesting questions around the adaptivity of our algorithm. And yeah, that's basically all I have to say. Thanks so much for listening. And now is a good time for more questions.
Yes. Yeah. Thank you very much for a wonderful talk with some very interesting results. Yeah, I think we have plenty of time for questions and discussions. So if you have question or comment, please feel free to unmute and ask now.
I am interested in the target state is a mixed state case. Does previous work study such a scenario in the quantum state setting?
So there's a result that in that case, in the worst case, you could need exponentially many copies to certify, even with adaptivity in your measurements. But I don't know if there's too much work on specific subclasses of mixed states that you can certify efficiently.
I see. Thank you.
I guess I should be clear that that's not even that's not even a single qubit result, actually. That's just in general. That's just with any arbitrary measurements, you already need exponentially many copies.
I see.
I guess in the mixed state setting, you would also need to maybe change this metric, right? I mean, the analog is you have a trace rho sigma, but that doesn't necessarily become 1 when sigma equals rho. So
yeah, I guess that's true. So you'd also, yeah, I guess you'd have to see what the right way to even define the problem is. I guess I was told that it's just possible. It's just not possible to do, but I didn't really even think about what that quite means.
Yeah.
I guess trace distance might be better because in the classical case, identity testing is somehow analog of this problem. But in their setting, I think they use total variation distance. So maybe trace distance might be a better measure, I guess. I'm not sure.
Yeah, that makes sense. But it might be, yeah, sounds like it might be hard.
Yeah, you'd probably definitely have to do things very specific to each, for very specific groups of mixed states and try to work with very specific classes of mixed states.
But I think that even in the very simple setting, for example, say uniform distribution, I think exponential many copies is necessary. So it is very hard to achieve, hard to find specific class of which can be achieved within polynomially many copies.
I guess like the uniform distribution is pretty hard to distinguish from the distribution where half of the things are twice as likely and half of the things are like not likely are like zero probability. So that's probably some intuition.
Maybe.
So yeah, even classical, sort of like a classical analog sounds pretty hard.
I have some kind of, I guess, like naive question. So is the way that the algorithm works, I can actually reject early? I probably cannot accept until I'm done running it. But is it sort of like, if I'm seeing enough failures, I would be able to reject?
Yeah, well, okay. I guess if you're going for no tolerance here, like you're just trying to accept if they're exactly equal and reject if they're like not equal, then yeah, you should just be able to like run an algorithm for a really long time and like reject the first time you get a rejection. But I think if you want to amplify so that you accept if it's 1 minus epsilon over n fidelity and reject if it's 1 minus epsilon, then I think you probably need to run it for basically the whole time in each case. Like maybe not quite the whole time, because you can reject if you get like more rejections than I guess you can probably reject early if like you can probably reject early if like you can prove that like at this point it's very unlikely that the fidelity was 1 minus epsilon over n. But probably if you're getting close to the threshold, you can't reject early with high probability. So it depends whether you want tolerance, I guess.
Yeah, I see. And okay, maybe another thing is like, so this is like for an arbitrary target state. So, but knowing this algorithm now, is there some improvement that you can get for like subset of states if you have some additional information of your target state or some restriction on it?
I guess like we know psi beforehand, so it's like our algorithm is designed based on like the algorithm has full information of psi before deciding what to do. Like we're sort of assuming that. But but I guess you're asking you're asking the question like, are there better algorithms for specific types of states? And the answer is definitely yes. Our algorithm is bad on product states. Like our algorithm is definitely suboptimal on product states.
So at the start of your talk, you mentioned like this problem for special classes of states. And in particular, you talked about stabilizer states. I was just wondering, is there a good certification problem for stabilizer states that's better than just learning the whole stabilizer state? Like, I mean, I know it's pretty easy to learn the stabilizer state. You don't need like
it might be the same as the learning algorithm. I realized actually, like based on a comment I got when I gave this talk previously, that not actually sure that algorithm that I talked about, that I like claimed in that slide, is like a single qubit certification algorithm. It might be a 2-qubit certification algorithm, and then it might be the same as the learning one.
What was the algorithm, by the way? Because you just had the initial, so I didn't really know what paper it was.
Honestly, I don't remember which paper it was either. I think it might just be the learning algorithm for single qubit, or for that though.
So that's the Gross paper, or?
Let's see. It's probably on here. Okay, I guess it might be one of these, but I'm not sure. It's probably not super hard to look up learning or certifying stabilizer states.
Okay. Yeah, no worries.
Yeah, sorry.
Yeah, I think I know there's one by Montanaro, right? But that uses like Bell sampling, so you actually need 2-qubit measurements. But I don't know if that's what you, probably not.
Yeah, I think it's possible that slide is slightly inaccurate, and the work I was referring to uses 2-qubit measurements, but I'm not actually sure.
Oh, and in that case, like, maybe following up from that. So this is like for single qubits. is there some kind of improvement that you can get if you allow like a few qubits, like 2 qubits or 3 qubits?
Not that we know of. Like when we first started this project, we would have been happy to come up with any like few qubit measurement algorithm. There basically was nothing that like used like any reasonable class of simple measurements and actually got all state psi. I guess reasonable class would be few qubit measurements here. So I don't think there's anything for like, you know, like 10 qubit measurements either.